So, welcome to today's class in Mathematics 1. Please take your seat so we can get started. So, we'll start with two brief organizational announcements. First, I've already mentioned that we are going to do an evaluation of this course, so you are going to evaluate me. To be able to do so, I need you to enroll for the course on TUM online. So if you have not done so yet, please do that today. I'm going to export the data tomorrow morning, and then we can't change that anymore. The evaluation itself will probably take place sometime in December, beginning of December. But I need to export the data early on so it can all be prepared. So please enroll for the course on TUM online if you have not done so, otherwise you will not be able to take part in the evaluation. Question? No, I'm not referring to the Moodle course, but instead the course on TUM online. If you're on the Moodle course, you are probably enrolled in the TUM online course already. Yes, it's for this lecture, so just for the lecture. No need to enroll for the exercise classes, just for the lecture, please. I'll use that to export the data for the evaluation. All right, second announcement. It seems the schedule hasn't been that clear with respect to the question when to watch which videos for this course. So just to clarify this once again, the idea is that you watch the videos for each week before we talk about those topics in class. So this is week 5. We'll be talking about inverse matrices and determinants this week. And that means you should have watched the videos for week 5 last week. The videos for week 6, next week, are online already. And the idea is to watch these videos sometime this week so that you'll be prepared for the discussions next week. Right? So always watch the videos 1 week prior to the classroom discussions. Also, the exercise sheets are online at the same time. And you should take a look at the exercise sheets and at least try to complete the homework problems to see which questions you might have, where you have difficulties, or if you master everything. The idea of the homework problems is to be kind of at an introductory level that you should be able to master after you've watched the videos, or at least you'll get an idea of where you might still have questions. All right, so watch the videos, try to do the homework, and then in the coming week, in the next week, we'll always discuss all of this in class. If you have not prepared with the videos, you will probably find my pace a little fast. Right, so the idea is to watch those beforehand, then have the class discussions, then do the other exercises, then ask any more questions that may still remain. All right, so I hope that clarifies things a little. Now, before we get to this week's topics, I've been asked to take another look at exercise 4.6. Maybe I can let you take a look at that as well. This one here, right? Consider a certain matrix. It doesn't really matter what the matrix is. The idea is pretty general. And the question here was, can we express a couple of operations on the matrix as multiplication of A by a suitable matrix? And it will help to understand how matrix multiplication works on the matrix itself. So I'll just give you a very quick overview of this problem here. So first task, part A. The objective here is to express a linear combination of the columns of A with some coefficients that are given as matrix multiplication. So columns of A are these here. Just write those down. And what we want is, we want a linear combination with specific coefficients, mu1, mu2, mu3. So I want to be able to express this as the multiplication of the matrix A and some other matrix. And let me write that out. So here's the matrix A once again. What we can do here, well, you do remember that the outcome of a matrix multiplication, the sizes of that outcome, are determined by the two matrices I put into that multiplication. The left matrix determines the number of rows, and the right determines the number of columns of the result. And the middle dimensions of those two factors have to agree. So in this case, we want a 3 rows outcome and 1 column outcome, right? We add those vectors, so the result is a vector with 3 rows, 1 column. So we already have 3 rows here. That looks good. We have 3 columns. So this matrix can possibly be the left-hand side of our operation, but not the right-hand side. Otherwise, the result would have 3 columns, and we don't want that. The 3 rows are fine. So what we need is, on the right-hand side, a matrix that has 3 rows, because we have 3 columns, right? So we need 3 rows for that middle dimension to agree. And we want the outcome to be 1 column. So this is in our to the 3 by 1, specifically 1 column. So this factor must have 1 column, so that the sizes will work. With this in mind, it means we multiply this by a vector. Where what happens if I multiply a matrix by a vector? Basically, that first entry here is multiplied for the first row with this entry, for the second row with this entry, for the third row with this entry. So the first entry of that second matrix always affects the first column of the first matrix. And what I want is to multiply the first column by mu1, and that's why I put a mu1 here. And same thing for the other entries. The second entry of that vector will always be multiplied with an entry in the second column of my matrix. And I want that second column to be multiplied by mu2, so that's why I put mu2 here. And same thing for the third column, right? So this is just matrix vector multiplication, basically. Matrix times a vector with the vector on the right is the same thing as doing a linear combination of the columns of the matrix. And the entries of my vector are the coefficients of my linear combination. Rows work similarly. So for part B, what I want here is a linear combination of the rows of A, where that means the outcome is going to be a row, so a 1 by 3 matrix, and that means A now has to be on the right-hand side of this operation, right? So I'm going to have 2 factors. The right factor is going to be my matrix A. The left factor is going to be a 1 by 3 vector, so that the sizes of the outcome are correct. And more specifically, what I have to do here is I have to put, what do they call this, lambdas? I have to put these coefficients here as a row on the left. And then what happens is when you do the multiplication, you always take a column here, multiply it by this row here, and that's the only row we have. So this entry will be multiplied by lambda 1. This entry will be multiplied by lambda 2. This will be multiplied by lambda 3. Same for the second column, right? So those go together. And same for the third column. So the entry in the first row is always multiplied by lambda 1. The entry in the second row is multiplied by lambda 2, and so on. Right? So you get exactly a linear combination of the rows, and these are the coefficients of that linear combination. And for the rows, you have to multiply from the left. Right? So multiplying a matrix by a vector on the right gives you a linear combination of the columns. Multiplying by a row vector on the left gives you a linear combination of the rows. All right, and once you got the hang of that, the rest should be pretty easy. So for C, we aim to multiply the third row of this matrix A by the factor 1/2. So that means if we're working on the rows, that means the matrix that we multiply A with will be the left factor. So A is the right factor. And the outcome should look like this. And now the third row is being multiplied by 1/2, so that will change. So the first two rows are unchanged. And what we have to do here is, of course, use almost the identity matrix. Right? If I do this, then this row times this column will be this entry. This row times the second column will be this entry. This row times the third column will be this entry. So by having this 1 here, we just reproduce the first row. Same thing for the second row. This here will produce the second row of my result, so we just reproduce the second row. And for the third row, almost the same thing. If we wanted to just reproduce it, we would do the same thing, identity matrix. Now we don't want to reproduce it, but instead we want to multiply it by not 1, but instead by 1/2. So we just put that factor here. Right? And that will do exactly the same, the right thing. Okay, I guess you can figure out D by yourself. Maybe just a quick look at E. So in E, what we want to do is we want to swap the first and the second row. So second row goes here, first row goes here, and the third row is unmodified. And again, we're working on the rows, so we have to multiply our matrix A by something from the left. This something will have to be a 3x3 matrix, because otherwise the sizes of the outcome wouldn't work. The third row goes unmodified. We just discussed that. So in the third row here, we just put our unit vector. And again, if we produce the entries in this third row, those are produced by multiplying this third row by all the columns of A. Right? And when we do that, this third row times this column, we always hit the last entry with this 1 here, and the others with zeros. Right? So it just reproduces the last row. It's just what we want. Now for the other two, what we need to do here is, in the first row here of the result, we want to reproduce not the first row, but the second row of A. Well, how do we do that? Well, remember what we did here. This here reproduced the second row. So we'll just use that vector and put it here. And doing that means the first row of the result will be produced by this first row here, multiplied by all the columns of A. And what does this first row do? Well, if I multiply that by one of the columns, this one entry hits the middle entry of the column, the second row. And all the others will be 0. So what I get is this 2 entry. For the second column, I get this 1 entry, and for the third column, I get this -1 entry. So I get exactly this second row, but I get it here, because I put that in the first row on the left-hand side. And of course, to get the first row of my A matrix, sorry, this one here, as the second row of my result, I just have to put this vector here. Yeah, so this, again, this selects the first row, and it's in the second row of my left matrix, so it will produce the second row of the outcome. So that's how I swap rows. And again, you'll figure out how to do the same thing for columns. Hint, just exchange the order. All right, I hope that clarifies for 6, at least a little. We might come back to that at some later point. Any more questions at this point before we go on to the rest? Yes. So the question is it possible that there is a mistake in the solution sheet? And the answer is yes, of course. I don't have the solution sheet here. I'm not quite sure about the numbers right now off the top of my head. So maybe you could just post a message to the Moodle forum or write me a quick email about that, and I'll check that afterwards. And if necessary, I'll be happy to upload a corrected solution. So if you find an error with the solutions, just let me know. I'll be happy to correct those. I hope there's not too many errors in there, but there's always the possibility, of course. Good. Let's have a look at today's sheet number 5 then. So today we're talking about inverse matrices, and probably we'll talk about determinants tomorrow. Let's start with a first look at the homework problem. So question here was to compute the inverse matrix. And before I go into detail about inverse matrices, I'd love to know who actually did that problem and what you got. So here's a Moodle quiz. Let me just switch that so we can have the tweetback. Sorry, not a Moodle quiz, a tweetback quiz. We can have a tweetback URL here. So I'm asking for the first row of your result for the inverse of A. I hope you have that written down somewhere. So we can hopefully check if your result is complete and correct. And I'm also asking for the difficulty, as usual. All right, I'll give you a couple more seconds, 20 seconds. And let's first take a look at the difficulty. So apparently most of you found that fairly easy, and that is, of course, what I was hoping for. Some found it hard. I hope you won't find it hard anymore after you've practiced that a little. And let's see, your solution is right, after all. Most of you got 9 minus 2, 0 as the first row of the inverse, and that is correct. So if you got that first row, hopefully the rest will also be right. Okay, wonderful. Then let's take a quick look at the slides and our theory of inverse matrices before we do some more practice on those problems. Now, the general idea with matrix inversion, you remember we introduced the multiplication for matrices last week. It works not quite the same as with real numbers. There are quite a lot of differences. But still, one can ask the question, is there something like an inversion? Is there something like a division of matrices in a certain way? And more formally, for real numbers, we know that we have a neutral element, that's number 1. A neutral element just means multiplying anything by 1 will not change that anything. And the question for inversion would then be the other way around, to see, well, if I have a real number a, is there a real number b such that a times b is 1? So can I get that neutral element from every starting point? And this b would then be called the inverse element of a, usually denoted by a to the minus 1, sometimes by 1 over a. And for real numbers, you know that almost always exists. There's one exception, and that is the number 0. So we can invert everything but 0. For matrices, one can, of course, ask the same question. In this case, the neutral element of multiplication is the identity matrix. So anything multiplied by the identity matrix will just stay the same. So the question will be, for a given matrix A, is there some b that satisfies a times b is the identity matrix? And you do remember that matrix multiplication is not commutative, so the order matters. And that means, to be precise, you'll have to ask the same question with the inverted order, right? So we need to have a times b equals in, and we need to have b times a equals in. And at this point, it's not clear that both will yield the same b. We'll find out that this is actually the case, if it's possible at all. Of course, if that is going to work, if both is going to work, and if the result is always in, that means A must have n rows and n columns, so it's going to be a square matrix. Right? So the first restriction that we want, or that we need, is this definition, this question only makes real sense for square matrices. So we can possibly define an inverse for square matrices, but not for all the others. So let's go ahead with the definition. We just say a matrix is called invertible if it satisfies both of these equations. A times b equals in and b times a equals in. And this matrix B is then called the inverse and usually denoted in the same way as with real numbers, by a to the minus 1. We usually don't write something like 1 over a. Never do that, please. We'll always write a to the minus 1. Or instead of invertible, you will often encounter the words regular or non-singular. That means the same thing. Matrix is invertible or regular or non-singular. And the opposite of that is a matrix that is not invertible or singular or non-regular. Yeah, again, those three mean the same thing. It's just different terminology. Depending on which book you read, you'll encounter one or possibly all three of those. All right, so here's a very quick example. We have this matrix A and this matrix B, and if we multiply them, A times B, just do the computations and you'll find out that actually, well, you get the identity matrix, and this also works in inverted order. You'll also get the same identity matrix. So this matrix A here, that is invertible, and the inverse looks like this. Right? So matrices that are invertible apparently exist. And it's not very clear how I got that inverse at this point. So that doesn't seem to be a very clear rule here, but we'll investigate that later on. On the other hand, if we look at this matrix here, we can find out that this does not have an inverse. And we just verify this by trying to find the inverse and just take a general B. We know that B has to be of the same size, so 2 by 2 matrix. So we just take a general B, we carry out the matrix multiplication A times B, and we get this result here. And what we see is the second row is an all zeros row. And of course that is because this second row here is an all zeros row, right? So that produces the second row of the outcome. Just seen that in 4.6. So specifically, that can never be the identity matrix because it has a 1 in this position here. So this is an example for a matrix that is not invertible. Okay, so apparently both exist. There are invertible matrices and there are non-invertible matrices. And we need to find out which is which and how we can determine that. And also how we can compute the inverse if it exists, of course. But before we do that, first thing that we want to make sure is that the inverse, if it exists, is unique. Right? So if I give you a matrix and I'm asking for the inverse, you will not get different results. You'll always get the same matrix if you don't make any mistakes, of course. Right? So we proved that. Inverse is always unique. And then we've discussed a few rules for matrix inversion. So before we discuss the question of when a matrix can be inverted and how the inverse looks like, let's first take a look at a few computational rules that may make it easier to answer this kind of questions. Now, if a matrix is invertible, then of course its inverse is also invertible, and it does what you'd expect it to do. The inverse of the inverse is, again, the matrix itself. Yeah? Same with real numbers. 1 over A is A. So if you invert twice, same thing as not doing anything. And there's also a neat thing about transposed matrices. If you have a matrix that can be inverted, then its transpose can also be inverted. And it's easy to get this inverse. So that can be obtained by just taking the inverse of A and then transposing that. So in other words, these two operations, transposition and inversion, are interchangeable. It doesn't matter which you do first. Sometimes we'll use a shorthand, but only rarely for this. A to the minus 1 and then transpose. We'll sometimes abbreviate that as A to the minus T. But not very often. Just in case you encounter that somewhere else, you know what it means. And then, of course, you can also ask, what about the product of matrices? Well, if you have two matrices that are invertible, the product is also invertible. And the inverse of that can be computed from the inverses of the single matrices. Similar to transposition, the order changes if you do that. So if you have AB to the minus 1, that's the same thing as B to the minus 1 times A to the minus 1. So the order is reversed if you take this inversion inside, in a way. Yeah, you remember the same rule holds for transposing matrices. All right, I'll skip over the proof here. You've seen that in the video. And the next theorem, that is probably the most important fact about invertible matrices or non-invertible matrices. We can prove that a matrix is invertible if and only if its rank is n, so it has full rank. Right? And that is the difference between those two matrices that we've seen before. Somewhere here. Where was that? Here, right. So you'll notice this matrix here. This is in row echelon form. and it has one pivot element but two rows, right? So that means the rank of that matrix is 1 and not 2. Oops, sorry. So rank of A here is 1, and that is not 2. So it does not have full rank. Come on, no. So at this point, using the theorem, we would already have known this matrix is non-invertible. For that first example here that we looked at, this 1, 2, 2, 3, or if you go on to compute the rank of that, you could bring that into echelon form. Let me just do that very quickly by just subtracting 2 times the first row from the second row, and that would give you a 0 and a -1. And you'll see that we have 2 pivot elements. So that means the rank of this matrix is 2. So this matrix has maximum rank, right? Can't be larger than 2 because we have a 2 by 2 matrix. And that means at this point we know there is an inverse. The matrix can be inverted. Right? So you can invert matrices if and only if they have full rank. And that means the rank is equal to the number of rows and columns. All right. Now that gives us a nice criterion about how to find out whether we can invert a matrix. We know how to determine the rank, and it's actually computationally easy to do that. So we can find out whether an inverse exists or not. The remaining question is, how do we compute the inverse? And nicely enough, both of these can be done in a very similar way. Now, if you want to compute the inverse of a matrix, what we have to do is we have to find a matrix B that satisfies this equation here. Well, what does that mean? Let's say this B here that consists of columns. We'll call those B1, B2, and so on to Bn. So those are the columns of our matrix B. And then what we do here is the first column of the outcome of this A times B is obtained in this way, right? So the first column of the outcome is always obtained by the first column of the right factor. The left factor determines the rows, the right factor determines the columns in a way. So this here is going to be the first column of our outcome. So this is the first column of A times capital B. When the first column on the right-hand side of our equation is the unit vector u1, right? 1, 0, 0, 0, and so on. That's the first column of this. So if you want to satisfy this equation, then specifically this equation needs to hold. Same thing holds for the second column. Second column of the outcome is determined in this way by using A times the second column of our B, right? So that's going to be the second column of A times B. And similarly, this U2 is the second column of our IN. Right? And of course, those two need to agree if this equation will hold. So that means we also need to satisfy this equation here. And the same holds for all the other columns up to the last one. So this is the equation for the last column of B. Right? So remember, B is our unknown. We want to determine B or find out if it exists at all. But let's assume it will exist. We want to determine it. Then what we have to do is we have to solve this equation system to get the first column of B. We have to solve this equation system to get the second column of B, and so on up to this point. So that means we just need to solve n equation systems. We know how to solve equation systems. It's all just Gaussian elimination. So again, that should be easy. It becomes even easier by the fact that the left-hand side, so the coefficients here, is always the same. We always have the same A. It's just the right-hand side, this U1, U2, U2, and that changes, right? So in particular, that means the manipulations that we do, well, those are governed by the left-hand side, right? So we always do the same thing on the left-hand side. Just the effect on the right-hand side will be different because the starting point is different. And that means what we do is effectively, we solve the same system n times just with different right-hand sides. So what we could do is just do all the Gaussian steps once and apply them to the right-hand sides all at the same time. Right, so solve once and apply all these Gaussian elimination steps to all right-hand sides at the same time. And that's exactly what we do. So what does that mean? Well, we start with a tableau that looks like this. We have the A as the left-hand side, and then we have all the right-hand sides at once. And stacking those next to each other just gives us the identity matrix IN. Then we do Gaussian elimination procedure. And to be able to read off the solution even more easily, we won't stop at echelon form, but instead we go on to obtain reduced echelon form. And remember what reduced echelon form means? Well, that means that on the left, so in this coefficient matrix, we not just get the staircase thing, right? So that would look something like this here. Here's our pivots. We have zeros below here. No, sorry, that is not supposed to be here. And in addition to that, for the reduced row echelon form, there's two other things we want. First, instead of arbitrary pivots, we normalize to ones. And also, in addition to having the zeros below the pivots, we also produce zeros above the pivots. Right? So that's the other addition. We also have zeros up there. And if you have a form like this, you can just read off the solution, because solving an equation like this is very easy, right? So xn is just, well, the right-hand side, x3 is equal to the right-hand side, x2 is equal to the right-hand side, x1 is equal to the right-hand side. The other variables don't play a role in each of these equations anymore. One equation per variable, right? Simplest thing you can get. And as we want to solve n equations of the same type, it pays off to do this extra work. And basically what that means is this left-hand side, this coefficient part, is now in the form of an identity matrix. It looks like this. And the right-hand side, well, all those right-hand sides will form another matrix. And you can now read off the solutions directly from that matrix. So the columns of this matrix will now be exactly the B's that you wanted. Right, so in other words, this here is the inverse that we wanted to have. Okay? So basically it's just Gaussian elimination. You just do several right-hand sides at the same time. And you produce reduced row echelon form, and then you can just read off the inverse matrix. Also, in case the matrix, this A that you start with, if that turns out to be not invertible after all, you'll find out. Because during this Gaussian elimination step, you'll get n pivots, and then you know, well, we have full rank, so it will work out. Or you will, at some point, get a row that doesn't have a pivot. And in that case, you can stop because you know, well, the matrix doesn't have full rank, so there is no inverse. No need to carry on. And what happens, in other words, is you'll get a 0 row somewhere, and the right-hand side will not be 0 for some of those columns on the right-hand side, so it will turn out that it will not be solvable. Right, so in other words, with this procedure, you can just start, and either you get this result in the end, and you have your inverse, or you will get a proof that there is no inverse. No need to determine that beforehand. Of course, you should only do this if you actually want to have the inverse. If the question is only, does the inverse exist, there might be easier ways. Right? And if you can find an easier and faster way, you should, of course, take that route. But this always works, regardless of whether A is invertible or not. It either works, or you'll find out it doesn't work. And then you also have proof that it can't work. All right, so that's the general procedure for computing an inverse matrix. Here's a brief example where we did just that. We want to see if this matrix here can be inverted. And if so, we want to find out what the inverse looks like. And what we do is we start with this matrix on the left and the unit vector, so the identity matrix on the right, 3 right-hand sides at the same time. And then we just do Gaussian elimination steps, right? So here we have a 0 here already, so no need to change the second row. We'll use this pivot element. We'll subtract the first row here from the third row to get a 0 here. And please don't forget to do the same manipulations on the right-hand side as well. Sometimes people forget that, and that, of course, will yield the wrong result. Then you go on with this pivot element here. And in this case, I found this 2 to not be too convenient to work with. I'd rather have a 1 or a -1, so I opted for changing the rows first. And of course, you can do that, right? Changing the rows just means changing the order of the equations. And remember, basically, we're solving n equations at the same time. So changing the order of the equations doesn't change what we are doing here. It doesn't change the outcome in particular. So that is totally fine. We can change the rows if we want to. And I did that here. Again, don't forget to also take the right-hand side when you change those rows. Next step I did is I normalized this to +1 by multiplying the whole row by -1. I need to do this normalization anyway at some point, so why not do it now? And that means I get a +1 here. Again, don't forget to also manipulate the right-hand side. And then I use this pivot element to produce a 0 down here. So that's what I did here. And you can see we're almost done. This second row is already looking good. This last row, that needs some normalizing, so we need to get a +1 instead of a -1 here. That's easy to do by just multiplying that row by -1. The first row still needs a little work. And we start with eliminating that 4 here, so now we're working backwards. We use this pivot element here to start eliminating everything above it. Here we have a 0 already. Here we eliminate that 4 by just adding 4 times that third row to the first one. And as we have zeros here, that means we don't change anything in these entries. Just the last one will be affected. That's why we're working our way backwards now. Right, so here's the 0. Last thing we need to change is this -1 here. That's still in the way, so when we get to this pivot, right, again, we're working our way backwards, and we just add that second row to the first one to get rid of that -1 entry. And then here's our reduced row echelon form. And you can now see this has full rank, so A had full rank. And that means the matrix can be inverted, and this right-hand side here, this gives you the inverse of A. Right? So A is invertible, and this is the inverse. And just in case you want to verify that you're actually correct, what you can now do, of course, is you can multiply A and A to the minus 1 and see whether the result is actually I3. Right? That should work. Otherwise, you made a mistake somewhere. So if you have some time left to do that, it might help verifying this, or at least checking 1 or 2 entries to see if those work and to hopefully catch easy errors. All right, the second one, we'll talk about that one later. Maybe let's have a quick look at this third one here. Third example, this matrix here. And again, I'm applying the same procedure, right? I put the matrix on the left, I put the identity matrix on the right. I'm doing Gaussian elimination steps. And in doing so, at some point, I hit this barrier here where I get a 0 row on the left. At that point, I know the left-hand side doesn't have full rank. So that's when I can stop my procedure. At that point, I know this matrix, this cannot have an inverse, right? So I can just stop there. I can say, well, 2 pivots, the rank is 2, it's not 3. It should be 3 for inversion, so A is not invertible. All right, so once you find that your matrix is actually not invertible, that's where you stop. And of course, write a quick note. All right, that is all about the theory and practice of matrix inversion so far. Any immediate questions before we discuss a few examples? Then maybe let me ask a couple of questions of my favorite true-false type. So again, please take a look on Tweetback. There is 3 questions on there that I'd like you to answer. First one is true or false. The identity matrix is always invertible. Second, true or false. Only square matrices can have an inverse. And the third, true or false. Every square matrix of full rank has an inverse. Right, I'll give you 30 more seconds to think about that. All right, now let's take a look. First question, the identity matrix is always invertible. Well, the identity matrix obviously has rank n. I hope you find that obvious because we have n pivots. The 1 entries are the pivots of this matrix, so it is invertible, obviously. Okay, and most of you thankfully got that one right. Second one, only square matrices can have an inverse. We've discussed that at the very beginning. So if that definition is going to make sense, A times B is IN and B times A is AN, if we're going to make sense of that, of course, A and B have to be square matrices. Otherwise, it will not work in one of those two directions. And we want them both. You can extend that definition, by the way, if you only ask for one of those directions, you can extend those to non-square matrices, but we're not discussing that. It's not very useful. And the last one, every square matrix of full rank has an inverse. That was basically the central theorem of today. A matrix is invertible if and only if it has full rank. Right? So that is true. Square matrix of full rank has an inverse. And no other matrix has an inverse. It needs to be a square matrix and it needs to have full rank. All right, that worked well. So the homework you did, let me just have a quick look at that. First homework question, we've already collected some feedback on that one. That asked you to compute the inverse of this matrix here. You mostly got that right, so I guess it doesn't make sense to discuss that problem here. Instead, I suggest we take a different matrix to practice that one again, so that those who got it right will at least get some new numbers. So let's call that problem here. And that, by the way, that is from a 2020 exam. So that's even an exam, a very simple exam questions, I'll admit. And your task is to compute the inverse of a matrix A given as 1, 2, 0, 2, 2, 2, and -1, -2, 1. And I suggest you try to see if that has an inverse, and if you can find it. And then we'll take a look at the procedure together. So I'll give you a couple minutes to try that. Quick show of hands, who's done already? So once you're done, feel free to compare your result to your neighbor, given that he or she is done as well. See if you got the right answer. Remember, the matrix, the inverse matrix is unique, so you should all get the same answer. Right, I hope most of you are done by now. So let's take a quick look at the answer. In this case, A is invertible. And the answer that you hopefully got should be this one here. Unless, of course, I made a mistake. So very quick tweet back question. Did you get the correct answer? Yes or no? That should be quick, so I'll give you another 20 seconds to answer that. All right, so apparently most of you did the computations correctly and arrived at the right inverse, so I'm confident that my solution is correct. Maybe let's still have a quick look at how to do the computations for those that might have made a mistake somewhere. As you know, we'll start with this matrix A here, so let me copy that once. Oops, no, soon. Well, let me just write it down again. So this is 1, 2, 0, 2, 2, 2, minus 1, minus 2, 1. And for the right-hand side, we'll just use the identity matrix. And now I'll start with this pivot element here, the 1. And I want to produce zeros down there. There already is a 0 here, so I just need to eliminate this 2 here, and I do this by subtracting the first row twice from the second row. Right, so this first step, I'll copy the first row. Don't forget the right-hand side. For the second row, I get 0. Then I get 2 minus 4, that's minus 1. And I have minus 2 plus 2, that is 0. And again, don't forget, same thing on the right-hand side. So here I have 0, 1, 0, minus 2 times this row here. So that will yield a minus 2, 1, 0. And I'll just copy the third row. All right. Then this is going to be my next pivot element, the minus 1. And I want to eliminate that 2 here, so I'm just going to add that second row to the third row twice. And at the same time, I'm going to multiply this by minus 1 to get a plus 1 here, because I need to do that anyway. Right. I copy the first row. I don't change that. I multiply the second row by minus 1, so I get 0, 1, 0. And here I get 2 minus 1, 0. And then I add this second row to this third row here, and that gives me 0, 0, 1. And on the right-hand side, I'll get minus 4. 2 and 1, and I did something wrong, obviously, right? Where did I go wrong? Sorry? This one is wrong? That is wrong. I need to subtract. Yeah, you're right. That should be a minus 2. Thanks. Let's correct that. That is a minus 2. So that means I only need to add that once, and then it hopefully turns out correct. Yeah, still get the 1 here, but this will change, and this will change to minus 2, 1, 1. That's looking a lot better. Good. So, almost done. Third row is nice, second row is nice. It's just the first row that I still have to manipulate a little. And what I want to do here is I should start from scratch, right? Let's just start this all over again. I'm sorry about this. Sometimes it's just better to start from scratch. All right, did I copy that correctly? Yeah, that looks good. All right, so let's do this again. Again, I'll copy the first row. I subtract the first row from the second row twice, and let's see, I get 2 minus 2. I get 2 minus 4, so that's a minus 2. And I get minus 2 plus 2, that's a 0. And here I get a minus 2 and a 1 and a 0. And I don't change the third row, so let's do this again. Now that looks better. Let's add the second row here and multiply this by minus 1/2. So I get 1, 2 minus 1, 1, 0, 0. 0 plus 1, 0. And here it's 1 minus 1 over 2, 0. And here I get 0, 0, 1, and minus 2, 1, 1. And now that looks a lot better. All right. Good. Finally, let's take care of the first row. again, we're working our way backwards now. So this is the pivot element that we'll be using first, and then this one. So we're working our way back up from the last column. We'll use that to get rid of this -1 here. So we do that by adding the last row to the first one. And that means we get 1, 2, 0, -1, 1, 1. And we just copy the other two. And finally, we need to get rid of this +2 here. And we can do that by subtracting the second row twice from the first row. And hopefully that will yield the right result. So that will give a 1, 0, 0 here. I just copy all the rest here. And on the right-hand side, we will get a, let's see, a -3. Then -2 times -1/2 is a +1, so that's a 2. And here we have 1 + 0, that's a 1. And I just copy all the other rows. And that is the result I wanted to have. All right, sorry about the confusion. I hope it's still clear how you should approach that. All right, any questions about this problem here? Otherwise, we can discuss one more example if you want. Good, let's see which one is going to be a good next example. Maybe this one. So again, that's a problem from an exam. This one was a 2017 exam, to be precise. And the question was, consider the matrix A given as, and now this matrix has two parameters. One is called beta 30, that's the first row. The other is called alpha. So here we have -alpha, alpha 2. And here's the last row, 2, 4, -1. And your task is to determine values for those parameters for alpha and beta in the reals such that A is invertible with, and I'll give you the inverse matrix I want. A to the -1 is -7, 5, 6, 3, -2, -2, and 6, -4, -5. All right, so I'll give you a couple of minutes to think about how you solve this one. Quick show of hands, is anyone done already? Very good. All right, maybe let's take a quick look at that one together. First, let me give you the solution so I can verify whether you're right. You should get alpha equals -1 and beta equals 2. That would be the correct solution. So it can be inverted, and the a to the -1 is correct for alpha equals -1 and beta equals 2. Again, I'd like to know whether you got the correct answer. So please go on tweetback. All right, so here's the outcome. About 2/3 of you got that one right. So let's take a quick look at how you could solve that problem together. There's two ways I could think of immediately. The first one is the one that I'm not going to do here. The first one is you could, of course, just use the fact that a to the -1 minus 1. So if you just invert a twice, you would get a back. And you do have a to the -1, right? No parameters in there. So you could just invert that and then compare the result to a to get the right values for those parameters. Okay, that's one way. The other way that I could think of would be to use the fact that a times a to the -1 is the identity matrix, A3 in that case. And you could do this matrix multiplication and then compare the result to I3 to see which values for alpha and beta you need, and also verify that this works for all the entries. And this is the way that I was doing that, so let's quickly give that a try. A times a to the -1. Again, a is beta 3, 0, minus alpha, alpha 2, and 2, 4, -1. times, and a to the minus 1 is minus 736. 5 minus 2 minus 4. 6 minus 2 minus 5. And then if you do that multiplication, let's see what we get here. So first entry, this will be the product of the first row and the first column on the right. So we get minus 7 beta plus 3 times 5, that's 15, plus 0. Then for the second entry, again, we just do the first row here. That will be first row times second column. So we get 3 beta minus 6 plus 0. And finally, we get 6 beta minus 12 plus 0. So that's the first row. We get the second row by using this one here and multiplying it by all 3 columns of the right-hand side. So that means we have minus 7 times minus alpha, that's 7 alpha, plus 5 alpha, that's 12 alpha, plus 12. Then we get minus 3 alpha minus 2 alpha, that's minus 5 alpha, minus 4. Yeah. And then we have a minus 6 alpha minus 4 alpha, that's minus 10 alpha, minus 10. And finally, third row, that will be, let's see, minus 14 plus 20, that's 6, minus 6, that is 0. Then we get 6 minus 8 is minus 2 plus 2, that is 0. And 12 minus 16 is minus 4 plus 5, that's 1. And the first thing you should notice is that this last row here, that's completely independent of any parameters, is the way it should be. Remember, we want the identity matrix. And if that would not have worked out, then no setting of alpha and beta would have gotten us an inverse matrix of this, right? So that's the first thing you should observe, that that isn't a good fit here. Second, the first row only contains betas, the second row only contains alphas, so those are nicely separated. And we can just use any of these entries to determine the value of alpha and beta that we need. So for example, for this one here, we could just take this first equation here. And this must be equal to 1, right? So we know minus 7 beta plus 15 must be 1. And we can just solve this one for beta. And we get 7 beta equals 14 or beta equals 2. And now if beta equals 2, this is going to be 1. This is going to be 0, and this is going to be 0. So please don't forget to verify that the other entries also work out. You just need one to determine the right beta, but you need to verify that the other entries yield the correct values. Otherwise, you'd have to conclude no setting of beta will do the right thing here. And we can do the same thing for the alphas. Let's use this, oops, different color. Let's use this one here. And this needs to be a 0. So 12 alpha plus 12 needs to be 0. And of course, that means alpha needs to be minus 1. And if alpha is minus 1, this will be 0. This second entry will be 5 minus 4. That's going to be 1. And the last entry will also be 0. And again, don't forget to compare these values to these here to see that this does the right thing. That's actually something that many people forgot in the exam, right? They determined the right alpha and the right beta, but then they didn't stop to actually verify that these other values here and the last row would also be correct. And you at least need to mention that will work out. Okay, any questions about this one? Yes. What is the question? So A inverse is given, and what is the question? Yeah? I'm not sure if I got that right. So you're saying the inverse of A was given in the problem statement, right? And your question is, do we have to show that again? So do you have to prove that A is actually invertible? So actually the task here was more to see if there are values for alpha and beta such that this is actually the inverse of A. And if so, find those values, right? And that means you can work with either that or that. Yeah, that's basically the definition of the inverse, to see if there are values that satisfy this. And in this case, we did this here. And we ended up with these values, and we verified that using these values would actually give us the right numbers for all entries of our matrix. Yeah, also for the last row. So we verified that A with these parameter settings and A to the minus 1 are actually inverse to each other. And of course, there is always the possibility that there is no possible setting. That could be a viable answer. Does that answer your question, or did you mean something else? Great. Any other questions? Otherwise, I'd say let's call this a day, and I'll see you tomorrow when we discuss determinants.